Hello, so we're going to do that exercise about this map. It does sum up a lot of the concepts we are talking about in this lesson. So we've got this map called phi that takes a polynomial of degree at most 2 and gives you the polynomial defined by x times p prime minus p. Okay, the first question is just to settle the things a bit. So, what space does phi of p belong to? So, phi of p, we said would give you the polynomial where x times p prime minus p. And what is p? P is an element of R2 of x. That means that p itself is a polynomial of degree 2. So p can be written as p of x as ax2 plus bx plus c, okay, because it's a second order polynomial. All right, so if I apply my map phi, I will have to compute p prime, so p prime of x is just 2ax plus b, and I will get that phi applied to p. That gives you a function of x, and that's just going to be x times p prime, so x times 2ax plus b minus ax2 minus bx minus c, and so that's really something that can be written as 2a minus ax2 plus b minus bx, so that cancels out, and minus c, so that's ax2 minus c. Okay, that's a polynomial of degree 2. Okay, we could, without doing all these calculations, so that belongs to R2 of x. Okay, there's a small subtlety that I haven't really talked about because we haven't seen each other live. Is that when I'm talking about the polynomial in general, I'm using the big letter, and when I'm looking at the value of the polynomial, specifically for some point x, I'm using the small x letter. Okay, but don't worry, it's really subtle. I'm not going to bother you too much about that. Okay, so I didn't really need to do all these calculations to tell you that, because we could also do the reasoning by saying, well, p prime, if p belongs to R2 of x, I could also say that you know that the first derivative of a second order polynomial, second degree polynomial is going to be a first degree polynomial, so p prime belongs to R1 of x. Then x times a polynomial of degree 1 is a polynomial of degree 2. And subtracting a polynomial of degree 2, I get something that belongs to R2 of x. Okay, I didn't really need to do all these calculations, but here we have exactly what it means actually to apply p to a specific, specific as any polynomial of degree 2 can be written like x squared plus bx plus c. Okay, so phi of p belongs to R2 of x. So phi is indeed a map that goes from R2 of x and that has image in R2 of x. Next thing we want to prove is that phi is linear. So that was first question. Second question, is phi linear? So as usual, we are going to take p1 and p2, two polynomials of R2 of x. We're going to take lambda in R and apply phi to the linear combination p1 plus p2. That's giving me, according to the definition of map phi, x times the derivative lambda p1 plus p2 minus lambda p1 plus p2. Okay, so that's giving me, sorry, I've got the derivative. So, and you know that the derivative of a sum is the sum of the derivatives, so you will get lambda x p1 prime plus x p2 prime minus lambda p1 minus p2, which I can really rewrite as lambda times phi of p1 plus phi of p2, and so phi belongs to the linear space of linear maps from R2 of x into itself. Okay, that was question 2. Let's have a look. Question 3. What is the kernel of phi? So we can just start by definition. The kernel of phi is going to be all the polynomials of degree at most 2 such that phi applied to this polynomial is equal to 0, which 0, again, it's going to be, well, the 0 that belongs to the image of phi, so the 0 of polynomials of degree 2. Okay, so let's write that phi of p is equal to 0. Okay, what does it mean? P of x was equal to ax2 plus bx plus c. That's how I can write any polynomial of degree 2. So if, and we already did the calculation that phi of p of x was equal to the polynomial, that's what we calculated here. Phi of p of x is the polynomial given by ax2 minus c. Okay, so that's ax2 minus c. So what is that? If that belongs to, if p belongs to the kernel of phi, that means that ax2 minus c is equal to the 0 polynomial. Okay, so what does it imply? We know that it implies that a is equal to 0 and c is equal to 0. So what do we get? P belongs to the kernel of phi. It means that p of x is the polynomial where a, the coefficient in front of x squared, is equal to 0, and the coefficient the constant coefficient is equal to 0. So p of x is anything that can be written as b times x. Okay, so we can also say that p of x, or rather polynomial p, belongs to the span of the polynomial given just by x. Okay, any constant times x. All right, and then we can use to answer. So the kernel of phi, that's the answer to that question. The kernel of phi is all the polynomials that belong to this span. So this is exactly equal to the span of x. Okay, and so that we can directly answer the fourth question. So phi is not injective as its kernel is different from only the 0 element, okay, of R2 of x, because the kernel of phi is equal to a space that contains more than the 0 element. Here I'm using the theorem 15. And so finally, we also want to answer the subjectivity of function phi. So that's a question, actually. We're going to see that it is not surjective. Okay. So what do? We can use the theorem 17. We want to find what is the image of phi. And the image of phi is going to be given by the span of the image by phi of the standard basis of a basis of R2 of x. And so let's take the standard basis. Phi of 1, phi of x, phi of x2. Okay, so this is image of the standard basis of R2 of x. Okay, that is actually theorem 17. Okay, so let's calculate the image of the standard basis. What is phi of 1? phi of 1 is going to be x times the derivative of constant function 1, so 0 minus x, so that's minus 1, sorry, so that's negative 1. Phi of 1 is negative 1. Phi of x is going to be x times derivative of x, which is 1, minus x, which is 0. Okay, and well, we already know about that because we saw that the kernel of phi was spanned by this, so we knew that this would belong to this kernel of phi anyway. And then what's the image of phi x2? It's going to be so x times 2 x2 minus x, sorry, x times minus 2 times 2x minus x2, and that is x2. Well, we already calculated that. So that the span of phi of 1, phi of 2, of x, sorry, phi of x squared is the span of negative 1 and x squared.